Hey there, so this video lesson is going to lead you through the 4 practice stoichiometry problems that are on that worksheet that we passed out in class. It's the 15G worksheet. I think it's got 4 problems on it. The way that this particular little narration lesson will work is that each one of these sets of slides has 2 parts to it. Number 1, there's going to be a slide where we work through the problem, kind of decode the problem itself, and practice rewriting those equations, working on figuring out the products of a double displacement reaction, writing formulas, etc. And then the second slide for each one has to do with the actual stoichiometry, the math part of each one. So if you're really good with writing and balancing the equations, you can kind of fast forward to the second of each of the pairs of slides. But if you're still kind of weak on writing and balancing double displacement reactions, then that first slide is really important for you. So to get started here, I'm going to kind of review what the main things are that we're going to go through, kind of the problem solving steps. We're going to do this in every single slide that we do today. So keep that in mind. As we get started, there's a few things that you're going to probably want, like a periodic table, a calculator. You're probably going to want some solubility rules, whatever, those sorts of things, to kind of make sure that you're getting the most use out of this for your sake. Remember, I'm not doing this for my good. I know how to do these. This is for you to be able to learn and practice how to do these. So like I said, hopefully you've got these done and you're kind of following along. If not, make sure to take some time and check yourself along the way to make sure that you're getting the best out of this. Don't just copy it down. All right, problem solving strategies. What is it that we do every single time we do these sorts of problems? There's a set of steps that we kind of go through each time we do these. So number 1, the first thing that we always do is that we always have to write the balanced chemical equation. Every single time you have to check to make sure that the balanced equation is present. You need to use the balanced chemical equation. It's got to be there. Sometimes you have to write it yourself. Sometimes I've already given it to you. So in any case, that's always step number 1. Step number 2 is kind of reading the problem, where you're trying to look at what do you know, what do you not know. So kind of identifying your known and your needed. So that's basic, that problem solving step of reading through it. What do I have? What information do I have, and what am I trying to find? I'm going to skip down to number 4, actually, of my step here, because this is the 4th thing that we always do. Every single time we do this, we're always going to have this step in here. There will always be a multiple step, every single time. Steps 3 and 5 kind of vary depending on what we're doing with stoichiometry problems, but every single time in stoichiometry you have to balance the equation, know what you're trying to figure out, and then you need to have a multiple ratio in there somewhere at some point in time from the balanced equation. So steps 3 and 5 are the ones that are a little bit variable. Sometimes, or almost every single time, you have to find moles. So we might have to do this one where we're converting from grams to moles first, or more commonly in this particular chapter, we're converting to moles using molarity. But somehow, in order to do step 4, the mole-to-mole ratio, we got to get to moles. So like I said, might be from grams to moles, might be from molarity to moles. Step number 5, the last step, is to kind of make sure we figure out what our output unit needs to be. Sometimes your output is just in moles and you're done. Sometimes you have to do kind of a variety of other things, like you might need to go moles back to grams with molar mass. Or you might use moles and molarity to find something like this, milliliters, if you're trying to find a volume of a solution. So there could be a couple of other types of things that you might do in these. So this is our basic steps. Balanced equation, identify what you know and what you need to find out. Always do multiple ratio, and then sometimes you have to do some other steps to get either to a unit you need or from a unit that you're given. So that's the steps that we're going to use every single time. Here we go. Here's problem number 1. So here's our first example from this particular worksheet, which has to do with finding the amount of precipitate from a reaction between 2 solutions. We've got lead 2 nitrate and excess sodium iodide. So the first thing that we need to do is figure out how to balance our equation, figure out what that is. So what are the 2 chemicals that we've got? As I'm decoding my thing, I know I'm going to be forming some sort of a precipitate, and then I'm going to have a reaction between this solution, which is lead 2 nitrate. So I got to figure out what that is. Lead is that, and 2 means it's a 2 plus, and then I've got nitrate, and there's nitrate like that, and nitrate, if you remember correctly, is a 1 minus. So I've got to cross my charges down to balance it out, so I need parentheses, there's lead 2 nitrate. My other solution is excess sodium iodide, and excess simply means I have more than enough to go around. So we've got to write our equation for sodium iodide. Sodium is that, and it's a 1 plus. Iodide is an I by itself, and iodide's a 1 minus. And so that one's already balanced. The charge is already set. So now we know what our two reactants are. We've got a solution of lead 2 nitrate and a solution of sodium iodide. So what are our two products? This is the part that when we're doing these equations, we're always doing that sort of inside-outside kind of thing, where we're getting our two products from switching partners. It doesn't really matter which one you do first or which one you do second, but in this particular case, I don't know, I'll do the outside first. So our new products are going to be lead and iodine. And again, it doesn't really matter which one you do first, but I'll do this one, lead and iodide. Now what's important about this is that these charges here don't change. So when I have lead on this side and it's a 2 plus, my lead on this side over here is also going to be a 2 plus, and my iodide is going to be a 2 minus. So I'm going to have lead, which is still a 2 plus, and I'm going to have iodide, which is still a 1 minus. So now I have to finish this formula by balancing the charges, cross them down, and I have PbI2. All right, my other product, I'm going to have to write it on the second row because I don't have enough room, is going to take this one, the nitrate, and this one, the sodium. Remember, with nitrate, this 3 goes with it. That never changes because that's part of nitrate, but this 2 that's here is only due to balancing charges, so that one does not carry over to the other side. So I've got nitrate, which is NO3, sodium, which is Na. So here's my other product, Na, which is a 1 plus, and nitrate, which is NO3, which is a 1 minus. And with this one, my charges are already balanced because it's a 1 plus and a 1 minus, so I don't have to do any crossing down here. They're already balanced to go. And then I've got my products. So my products are PbI2 and NaNO3. Those are my two products. The last step that I need to take is to balance my overall equation to make sure I know that I've got the same things going in and out. Kind of start by finding my most complex molecule. My most complex compound here is probably PbNO3. That's the thing with the most atoms in it. So I've got 2 nitrates here. So I'm going to need to do that over on the right side. So I'm going to put a 2 over here in front of that. That gives me 2 nitrates as well as 2 sodiums. So I'm going to go back here, balance out my 2 sodiums. Now I have 2 iodides, and I have 2 iodides on the other side. So I've got 2 sodiums and 2 iodides. Here's my 2 iodides. Here's my 2 sodiums. That equation is now balanced. Last step, figure out what my precipitate is, because remember my reactions ask me how much precipitate do I form. This is where you're going to want to get out some solubility rules. Solubility rules, if you've got it on hand, that'll make your life easier, but a lot of the times, Cl, NO, and so we've got our shortcut solubility rules that we can use, the Nakel-Noso rule, which says that anything that's got sodium in it is soluble, anything with chlorine in it, or most things with chlorine are soluble. Nitrates tend to be soluble, and sulfates tend to be soluble. So using this rule, this thing right here, which has both sodium in it and nitrate in it, is most likely soluble. So that one right there is going to be aqueous, AQ, which means that's in solution. So if there's a precipitate, it's got to be the other one. The PbI2 has got to be our solid. So now we know what our precipitate is that we're trying to find. We have our balanced equation, and now we're ready to move on to the next step. So here we got, you can see I've kind of copied my balanced equation on here so we don't have to write it again. So now that we've got our balanced equation, now we can kind of do the next part of our problem solving. Our problem solving was to identify our knowns and our unknowns, and then we can start to think about moles to moles and all this stuff. So what I like to do is go and circle the parts of the equation that I actually know something about. So right up in here, I know some information about this lead nitrate. This one right here I've got information about. So I've got 425 mLs of this, and it's a 0.1 molar solution. I've got excess sodium iodide, that's this part, which means I have plenty enough to go around, so I don't really have to do any worries about this. And then the other part is the question is asking about how much precipitate could be formed. And remember, this was the precipitate, so that's what I'm trying to find. And when it asks for how much, that's my unknown, that's what I'm trying to find. And units for how much is always going to be in grams. So now that gives me a little bit of a clearer picture what I need to do. I need to convert my mole-to-mole ratio from PbNO3 to PbI2, from this one to this one. And I can see from my balanced equation this is in a 1-to-1 ratio. So that actually makes our calculations a lot easier. I'll do it the long way just so that we can practice it, but it's definitely a 1-to-1 ratio, so hooray. So our middle step is the mole-to-mole ratio. The step before that was we had to get to moles, and so I've got this information right here. I've got to get to moles from molarity and milliliters, and the way that I do that is by using the molarity equation. Molarity equals moles per liter, or molarity times liters equals moles. And I just did a little bit of algebra in there to rearrange it. So now I can actually just plug my numbers in to figure out how many moles of lead nitrate I have, and then I can convert from moles of lead nitrate to moles of PbI2, so that works out pretty good. So my molarity is 0.1. My liters is 0.425. Please don't forget to convert that to liters so that you can actually have the correct answer on this one. Otherwise, your calculations are not going to come out pretty well. So by the time I do this out, my moles here is 0.0425 moles of PbNO3 too. NO3, 2. There we go. So now that we have the moles of our first compound, now we convert from the moles of the first one to the moles that we're trying to find. So it's our mole-to-mole ratio step. And we've got 0.0425 moles of PbNO3, 2. This is where I do my little wonder fraction. And I know in this case it's a 1-to-1. I know it feels kind of silly to do this when I don't have to. But it's just in case it's not a 1-to-1, I like to build that practice. So mole PbI2. And this is moles of PbNO3, 2. So now I've got my mole-to-mole ratio done, and I can do the last step that I need to. The last step that I would want to take care of would be to figure out how many grams I've got, because I've got moles, but again, the question up here, it's going to ask for the number of grams of precipitate, how much. So you can either do this as a separate step, or I like to do it in one single step. It's completely up to you, but this is where I'm going to put my moles down here, PbI2. And I'm going to put my grams of PbI2 up here, PbI2. This is molar mass. Molar mass of lead iodide, I think when I did it, it was 461.01. Yeah, it's a big number. But again, remember, molar mass is the mass of lead plus the mass of 2 iodines. Don't forget to put both of those iodines in there to get that total mass of 461. All right, so by the time I'm done here now, again, math-wise, multiply across the top, divide by the bottom. Oh, luckily these are 1s on the bottom, so that makes it really easy. So my math here is 0.0425 times 1 times 461. And when I calculate it all out, I get a number like this, 19.5929 something or other. I'm going to check my sig figs in my problem. What do I got for numbers up here? Right there I got 4 sig figs in 425.0. I have 3 sig figs in 0.100. So I need to round my answer to 3 sig figs. So the 19, I have to cut it off after this 5, but that'll round it up. So my final answer is 19.6 grams of PbI2 is the final total answer for that problem. There we go. All right, so how you doing? Here's problem number 2 coming up. Again, there's 2 slides for this. The first one I'm going to work out how to write the equation, and then the second one I'm going to actually use the equation to do the math. So this part right here, again, is just about writing the EQ out. If you're good at this, you can kind of sketch yours out and go into the next slide if you want to. All right, here we go. So what do we got in our problem today? We've got calculate the mass of solid sodium sulfate that must be added. All right. That must be added to, oh my gosh, 250 mils of a 0.2 molar barium nitrate solution. Okay, so I'm taking sodium sulfate and I'm adding it to barium nitrate. Those are my reactants. So sodium sulfate. Sodium is a 1+. Sulfate, you may not remember this or not, sulfate's SO4. The charge of sulfate is a 2-. Finish writing up my formula by crossing down because my charges aren't equal. Na2SO4, that's sodium sulfate. And then my second solution, or my other thing that I've got there, is barium nitrate. Okay, barium is Ba. Barium is a 2+ charge when you find it on the periodic table. Nitrate. Nitrate is NO3. It's one of our polyatomics. Nitrate is a 1-. So by the time I'm done with this, crossing my charges down, I need some parentheses and a little 2 there. So now I've got my reactants formulas written correctly. So does it make sense with my question? Mass of sodium sulfate that must be added to a solution of barium nitrate in order to precipitate out all the barium ions in the form of barium sulfate. What in the heck does all this stuff mean? So in other words, I'm going to take all these barium ions, I'm going to make them go away. And so on my product side over here, it's going to be barium sulfate is going to be one of my products. So I already know that one. That's kind of nice. Barium sulfate is going to be one of my products, BaSO4. Barium is a 2+, sulfate is a 2-, so that one's actually already set. So if I'm precipitating all the stuff out, that's even my solid. It's already given me that hint in the equation already. However, my equation's not done, and I know a lot of students like to stop right there and go, okay, I got barium sulfate, but remember there's another product. Whenever we do these double displacement reactions, we've always got an inside and we've got an outside, so you've got to make sure that you finish up your equation and do both of those. We already took care of the inside part, the barium sulfate, because again there's already a clue to that in the equation the way, or the problem the way it was worded. We've got to take care of this other thing, so we're going to have sodium nitrate is our other product. So again, my line's too long, so I'm going to write it on the second line. I've got to have sodium, which is a 1+, and I have to have nitrate, NO3, which is a 1-. Those charges are already balanced, so I don't need to do any crossing down because these are already set right here. So NaNO3 is the correct formula for my other product. And the last thing I have to do is to finish balancing the equation. So when I take a look at my equation over here, it doesn't really matter which one you pick is the scariest looking one. I see 2 sodiums and 2 nitrates on the left, so I'm just going to put my 2 out in front here to get those guys on the right, and that's now a balanced equation. So I know that's solid. I know this one is going to be aqueous because it's got both sodium and nitrogen or nitrate in there. So there we have now our balanced equation for this particular reaction. So now we can do some math with it because we have our balanced equation, and look, there it is. Yay! So now we got to figure out. Next part of our problem solving is to identify what we know and what we don't know. So we're trying to figure out the mass of sodium sulfate. So this is my sodium sulfate, and I'm trying to figure out the mass of this. So now I know that that's my grams. And it must be added to this much stuff of this barium nitrate solution. All right, so I know information about this one, 250 mils, and it's 0.200 molar solution. So now I know, in terms of precipitating out all the barium ions and all that kind of stuff, this one's not asking me how much barium sulfate I'm making. I know that's in the question up there, but that's not what this is asking about. It's asking me how much sodium sulfate do I need. So when I do my mole-to-mole ratio here, these are the 2 things that I care about in this particular problem. I don't care about any of this other stuff that's over here in the equation. It's here, and we had to finish out our equation to make sure we had the right mole-to-mole ratio, but we don't need to use these in our calculations right now. These are the only 2 things that we care about. So we're going to need to do our mole-to-mole step, which means I need to have moles of this. And again, with most of our problems that we're doing at this part of the year, we're doing this. Oops, sorry, wrote that wrong. Molarity equals moles per liter, or molarity times liters equals moles. By the time I algebra it out, so now I can plug in my numbers. My molarity was 0.200. My number of liters was 0.250. Again, I had to convert from milliliters to liters. Don't forget to do that. It's going to give you my number of moles. And in this case, when I do my math on here, it's 0.05 moles of barium nitrate. And O3, 2. There we go. Now, the next part, once I know how many moles of this I have, I need to do my mole-to-mole ratio. Luckily, my mole-to-mole ratio, again, is 1. I gave you another easy one on here. And it's 1 because there's a 1 here and a 1 here, so that's kind of nice. And then the last thing I'm going to need to do after my mole-to-mole ratio is convert from moles to grams. So I'm going to set up my little wonder fraction. Gosh, I hope I have enough room for this. But I'm going to set it up over here. 0.05 moles of barium nitrate, BaNO3, 2. I'm going to do my mole-to-mole ratio, so this is moles of barium to the moles of sodium, Na2SO4. These are 1 to 1 because the equation says 1 to 1 in NO3. And then the last step is convert from moles to grams, MOL to G of Na2SO4. I know my handwriting is terrible, I'm so sorry. By the time I figure all this stuff out, when I do the molar mass of sodium sulfate, I need to have 2 sodiums, a sulfur, and 4 oxygens all added up in there together. And the molar mass of that is, I believe it's 142.04. Yeah, by the time I do 2 decimal places all the way across. Again, that's 2 sodiums, a sulfur, and 4 oxygens, molar mass. So by the time I do all of this math out, by the time I'm done, multiply across the top, multiply, multiply, multiply this way, and then divide by my ones on the bottom, so I don't have to do too much there. 0.05 times 142.04 gives me the answer of 7.102 something or other in my calculator. I've got 3 sig figs in my problem. This one's got 4 sig figs. This one here has 3 sig figs. So my final answer in 3 sig figs is 7.10 grams of Na2SO4 is needed to precipitate out all of those barium ions. In other words, to react completely with all of this stuff, I need exactly 7.10 grams of this stuff to be able to make this stuff completely go away and turn into this stuff. That's basically the process that we're doing. Let's take a look at the second half of the question, because there's a part B of this one. Okay, part B says how much barium sulfate will be formed. Again, using the same information that we had before, it's kind of part B of the same problem. So we've got 250 mils, it was 0.200 molar, and I remember that when I did the math earlier, we did M times L equals moles. We had 0.05 moles of this stuff present. And now we're trying to find barium sulfate. So now we're trying to go from this one to this one. So this is my new question. How much of this am I going to make? So again, pretty much the same idea. It's just two different chemicals in use. Doesn't matter which 2 we use anytime we do Stoich. We can start from one reactant and go to any other type of thing that's in the problem in the equation. Doesn't matter which one it is. So 0.05 moles, set up my equation of barium nitrate, NO3, 2, sorry. What are we going to convert it to? Well, we're trying to convert it to BaSO4, so we need to use our mole-to-mole ratio. Moles of barium nitrate, BaNO3, to moles of barium sulfate, BaSO4. Oops, forgot that. It's a 1-to-1 ratio. Hey, that's kind of handy. I love 1-to-1 ratios. Makes the math so much nicer. And then the last step is because I'm trying to find grams up here, I can do one more step. I can cross this down and do my grams to mole step right here. If you want to, you can do it as a separate step completely. I like to do it as one. Moles of barium sulfate, 2 grams of barium sulfate. There we go, BaSO4. By the time you do all of this molar mass out, it's 233.43 grams. Yeah, it's pretty heavy. Barium's a pretty heavy element. You got the sulfur, 4 oxygens in there. Yeah, it's a pretty fast. So, math, again, multiply across the top, and then you divide by the numbers on the bottom. Oop, I forgot a number down here. It's 1. Remember, every time you do a gram to mole step, it's a 1 mole to that many grams. So, by the time we do the math here, we get a number of 11.6715, something like that's what my calculator gives out. Again, I've got 3 sig figs in my problem, so by the time I round it all out, it's 11.7 grams of barium sulfate, BaSO4, and is a complete and correct answer with sig figs and units. Okay, moving on. Okay, so here's our third problem. This one's written a little more challenging in terms of writing this equation out, but that's okay. It's good for you. You need the practice anyway. So let's take a look at what we got. Calculate the mass of some sort of blood red precipitate. I love that name. That sounds so scary. That forms when you've got 50 mils of this solution, silver nitrate, is reacting with 30 mils of this solution of potassium chromate. So there's what we've got. We've got silver nitrate and potassium chromate. We're going to form some blood red precipitate from there. So silver nitrate, let's start there. Ag, it's a 1 plus. Silver is always a 1 plus. NO3 is a 1 minus. So that one's done. Second reactant is potassium chromate. Potassium is K, it's a 1 plus. Chromate is CrO4. That's chromate. And it has a 2 minus charge. So now I have to balance my charges, cross them down. It's K2CrO4. So there's my 2 solutions. I've got a silver nitrate solution and a potassium chromate solution. And I'm going to form 2 different things. And one of them is going to be a blood red precipitate. I don't know what it's called yet. So again, remember when we do these, it's that inside-outside. So we've got our inside and then we've got our outside. Those are going to be our new products that's going to form. So we're going to have silver and chromate, potassium and nitrate. Doesn't really matter which order you write it in. I'm going to do the inside ones first. I don't know why I always do inside first, but I do. Potassium and nitrate, KNO3. Potassium's a 1 plus, nitrate's a 1 minus. So that's already balanced. I don't have to do anything to the charges there. They're already set. And my other product is silver and chromate. Silver is Ag, chromate CrO4. Silver's a 1 plus, chromate's a 2 minus. So that means I need Ag2CrO4. Cross them down to balance that charge. Okay, last step I need to do is to finish by balancing my entire equation to make sure the whole thing is correct so I can get my mole-to-mole ratio out of it. I see that I've got 2 potassium on the left. I've only got 1 potassium on the right, so I'm going to put a 2 here. You could start someplace else if you want to, but that's the first thing that just happened to catch my eye. I got 2 of those and only 1 here. So I'm going to balance those guys out. And now I've got 2 potassiums and I have 2 nitrates now. I also have 2 silvers over on this side, so I can put a 2 over on this side, and things are just going to magically work themselves out. I love when it works out like that. So now I have my complete balanced equation. Last thing is to figure out which one's my precipitate. Blood red precipitate. NaClNOSO, our shortcut solubility rules. Anything with sodium, chlorine, nitrate, or sulfate is going to be soluble. I see a nitrate right here, so this one's probably our soluble. That one is going to be our precipitate. So there you go. Our blood red precipitate must be silver chromate. Okay, let's do the Stoich on this. Next page. There we go. So we're trying to figure out what happens when we mix these 2 solutions together. So we've got information about the silver nitrate solution, 50 mils, and 0.250 molar of the silver nitrate. And then I have information, so that's this stuff right here. This information is about the other solution, 30 mils of 0.250, same concentration, molar potassium chromate solution. So whenever you know information about 2 different reactants, I know information about this one and this one, All of a sudden now that's a limiting reactants problem, and I'm going to have to do, grilled cheese, 2 different equations to figure out my answer. I'm trying to find out this, the grams of my blood red precipitate. So we're going to have to do 2 problems. So problem number 1 is going to be over here, and problem number 2 is going to be over here. We're both going to end up over on that other side. So start doing some math here. So both times when we do these, remember, we're always going to kind of start off with that molarity equation because that's useful for us. Where's my pen? There it is. So molarity equals moles per liter. Molarity equals moles per liter. And with doing these, I know that by the time I do the rearrangement of my algebra, I got 0.250 times 0.050. Again, 50 milliliters, move the decimal place over 3 places, gives me a certain number of moles of this stuff. How many do I have? 0.0125 moles of silver nitrate. For the K2CrO4, I'm going to do the same thing. It's going to be 0.250 because that's the concentration of this one. And now I have 30 mils, 0.030. By the time I math this one out, I get 0.0075 moles of that stuff. So I'm going to erase some of my work here just so I have enough room to finish out my math problems. So I'm going to kind of transfer some of my numbers up here. Hold on, what am I going to do here? I got to do that, I got to do this. I'm going to make some room for myself up here. So I get 0.0125 of that stuff and 0.0075 of that stuff. All right, let's see if I can erase some of this. What will it let me do here? There we go. Okay, so now I know how many moles of those 2 things that I've got. So this is moles up here, and this is moles up here. So I have to do my 2 different math problems. 0.0125 moles of AgNO3. And remember, what we're trying to find is our solid precipitate. So these are in a 2-to-1 ratio. 2 moles of this, AgNO3, can make 1 mole of Ag2CrO4. Last thing I'm going to do is I'm going to do my molar mass step, since I know I'm going to need grams anyway. By the time I do this whole thing out, the molar mass of this stuff is 331. 331.73 grams per mole by the time I add up 2 silvers and a chromium and 4 oxygens. So when I go back to my wonder fraction here, 1 mole of that stuff, Ag2CrO4, is 331.73 grams of Ag2CrO4. Yikes, that's a big number. All right, so by the time I do the math on this one, I've got that number times that number divided by 2. Don't forget to do that division part of the problem so you can get the right answer to it. We get 2.0733 is the answer to that by the time I calculate it out. All right, so that's the first half. There's the hard part, kind of. Now I have to do the second half. Remember what we did, this is grilled cheese. I considered this one, just considering this one, how much silver nitrate or silver chromate could I get? Now I need to do my other half of my problem using this stuff. How much silver chromate can I get? The nice thing is once you get these problems set up, they're actually pretty easy to do. So 0.0075 moles now of K2CrO4, the other stuff. These are in a, looks like a 1-to-1 ratio. 1 mole of K2CrO4 will produce 1 mole of Ag2CrO4. And the nice thing is my molar mass is the same. So 1 mole of Ag2CrO4 is still 331.73 grams of Ag2CrO4. Okay, so now math this out. Again, multiply across the top and then divide by the bottom. So when I multiply these, it's 0.0075 times 33 point whatever this is, divided by 1s, so that's not too bad. So by the time I do this one out, I get 2.4879 something or other as I keep going. So I've got 2 different answers here. Again, limiting reactants problem, you always choose the smaller number to be your theoretical yield. So that means my theoretical yield is 2.07 grams of Ag2CrO4. This is called theoretical yield. This is not the limiting reactant. Your answer is theoretical yield, so that's how much we should get. Our limiting reactant, by the way, is AgNO3. It's got to be a reactant. It's got to be one of the things that we started off with. So again, your answer can never be a limiting reactant. Something that you started with was, and that means that potassium chromate here was our excess reactant, and this number doesn't mean anything to us at all. There we go. So our final answer to this one, 2.07 grams of silver chromate. Once you get used to doing that grams to moles or that molarity to mole step, it's pretty similar to the things that we've done in the past. Just don't forget that you have to make that final decision about which one's the right answer, I guess, and then to circle or somehow indicate which one's the theoretical yield as opposed to the excess, whatever you would call that other number. All right, last problem. So this one's slightly different, not a whole lot. This one is that special case of acid-base reactions. In acid-base reactions, you deal with them just like anything else. We tend to kind of focus on the concept of neutralizing, and that word gets thrown in there. And that just simply means that we have exactly the right amount of acid and base to work out with one another stoichiometrically. So let's start with writing our equation. That's what we've got to do every single time. So we're trying to figure out what volume of HCl, HCl is hydrochloric acid. So I know I'm going to need to use that, is going to be needed to neutralize that much barium hydroxide. Neutralize here means react with BaOH2, and that's barium hydroxide. I know that this is an acid and a base reaction, by the way, because acids always start with hydrogen, and bases are always going to have hydroxides in them, so it makes it a little bit easier to recognize what they are. And our two products, again, it's a double displacement reaction, so we do inside-outside. So our inside is going to be barium and chlorine. So barium is a 2+. Chlorine, or chloride, is a 1-, so it's going to be BaCl2. Our other product is going to be hydrogen and hydroxide, HOH. In other words, water. But a lot of times I like to write it as HOH. It just kind of helps me remember what it is that I'm creating there. So hydrogen hydroxide, there you go. And this is always what we get. We always get something, what is it, acid-base reaction. We always get water as one of our two products. And the other product is something called a salt. In this case, the salt is, instead of being sodium chloride, is barium chloride. And that's the other product that we get. So when we're saying neutralize, we're saying how much of this stuff do we need exactly to react with this stuff. So we're going to be trying to figure out the amount of this is what we're trying to find. All right, last up is to balance the equation. I've got my formulas all written correctly, but my equation's not. I've got 2 chlorines over here on the right. I've only got 1 chlorine over here on the left, so I'm going to put my 2 out in front there. Now I've got 2 hydrogens on the left and 2 hydroxides on the left, and that means I need a 2 out in front here to get that whole thing to balance out. So there we go. So now it's just a matter of doing stoichiometry, just like any other problem. So here it is, time to do the stoich that we've got. Again, our next strategy is to identify what we know and what we need. We're trying to figure out the volume of hydrochloric acid. So we're trying to figure out this one, which is actually usually going to be in milliliters or liters is fine. And we know that it's 0.1 molar solution. And then we're trying to neutralize 35 ml of 0.250 molar barium hydroxide. This is still stoichiometry, and you can see the hint here is to solve for moles of hydrochloric acid first, and then we'll talk about how to kind of deal to get from moles to milliliters in a second. So let's do our thing like we've been doing. Molarity is moles per liter. Molarity times liter equals moles. So that means that we've got, if I remember correctly, 0.250 times 0.035. Again, you have to convert it to liters, don't forget that. 0.00875 moles of that stuff is how much we've got. And this is moles of barium hydroxide. So now this is a matter of doing our little mini stoich problem, our little wonder fraction to figure out what this is. We're going to convert from barium hydroxide to hydrochloric acid. So we're going this direction is what we're trying to find. It's not done any differently than the other ones that we worked out. It's just knowing where we end and where we're starting. So 0.00875 moles barium hydroxide, BaOH2, and that is in what kind of a ratio? We need moles of barium hydroxide to moles of HCl. And if I look at my equation right here, it's in a 2-to-1 ratio. 2 HCl is produced from 1 barium hydroxide, or reacts with, I should say. So 2 of these guys reacts with 1 of those. By the time I math this out, 0.0175 moles of HCl is how much we would need in order to neutralize that. So that's great. We've got 0.0175 moles, which is fine, and that's almost to our final answer. We've got the moles to moles step. Now we have a slightly different final step than the ones that we've done before. And the other ones we would just convert to grams of molar mass, but this one's asking us for volume. So with volume, we're going to go back up to this original information up here and use that because I have molarity equals moles per liter. And I have some of these pieces now. I've got molarity because that was already given to us. So I've got the molarity part. I've got the moles part, which is this part, and now I'm just going to be solving for this. So here's the problem, is that for some of you guys, it's going to be the algebra. So I'm going to rearrange it, write it like that, and I'm going to solve for the liters, get that by itself. Liters is moles divided by molarity. Again, it's just an algebra thing, but I see students do this upside down all the time. And now it's just a matter of plugging and playing. 0.0175 moles divided by our molarity, which is 0.1 molar, is going to give me a final answer of 0.175, and that's liters, also known as 175 ml, milliliters. So there you go. The last step here was just a little bit different than the other ones, where we had to convert it back to volume by using the molarity equation with the second solution. Not too much harder, just one extra little kind of a twist to the other ones that we've done. So there you go. I hope you had some, I would say having fun, but that's not the right word at all. Hope you had some success with working on these, and you had a little bit more practice with writing and balancing equations, and then doing those stoichiometry problems, especially including the ones that have molarity. All right, see you in class. Good luck with this.